Hello students, so today we will discuss about thermogravimetric analysis TGA and differential scanning calorimetry DSC. Now these tests are done mainly to find out the thermal properties of a material, especially they are used for polymers. Now this TGA DSC, where TGA stands for thermogravimetric analysis and DSC stands for differential scanning calorimetry, they come together. The instrument which is used, it has both the facilities of usually has both the facilities of TGA and DSC. But although they are both heat thermal analysis, but there is a slight difference between these two methods and the requirement of these methods, and in which condition are these methods used. Now, by TGA, which is thermogravimetric analysis, we basically measure the weight percentage of material loss due to heat. And what is left is the residual mass after this TGA test has been carried out. Now you can see here from the diagram which is given that both TGA and DSC plots have been given. The red one here is the TGA plot, so it looks something like this. We draw a rough sketch of the TGA plot. So you have this weight percentage on the y-axis and temperature on the x-axis, which has gone up to 1200 degree centigrade, and the weight percent, as you can see, has reduced from 100 weight percent to a certain number, and it has been found that the reduction in weight percent is about 20%. Now these tests are mainly, this TGA tests are mainly done to measure the thermal stability of the material, and in case of polymers especially, they are also used to measure the decomposition temperature in case of polymers. Now there are two different approaches by which you can you can perform this TGA test. The first one is called the isothermal approach or isothermal test, where the temperature is kept constant and the decomposition by means of percentage weight loss is observed as a function of time. This is called an isothermal TGA. Apart from that, you have another way by which this TGA test can be done, that is called dynamic TGA, where the rate of heat flow to cause a decomposition, this is varied. That is called a dynamic TGA. Now TGA are used especially for those materials which that means if you have a decomposition taking place and you would like to know at what temperature does this decomposition take place, whereas in DSC, differential scanning calorimetry, these tests is done to find out the endothermic and exothermic properties associated, or exothermic gas or heat flow associated with the phase transitions taking place in the material. So there is a slight difference between the two. Now, usually, if you don't know anything about the material, that means you don't know what is the material, absolutely no idea, then it's better to perform both of them. But if you have a certain idea that this material is going to decompose and you would like to find out at what temperature does it decompose, then your thermal TGA test is the appropriate test. And if you would like to find out, say, the glass transition temperature or the melting point or the specific heat capacity, then DSC is the appropriate test which needs to be carried out. Now let's now focus on how our DSC plot looks like. Differential scanning plot looks like. From the diagram given here, the blue one this is the DSC plot. So if you plot it separately, so you have milliwatt per gram in the y-axis, and you have a temperature in the x-axis, and you have a 0 at this point. So the plot has taken a shape which is something like this. It's gone down, gone up, and again gone down. This is the shape. Now this above and this 0 line, this line, this is considered to be the exothermic reaction, and below this line, this is the endothermic reaction. Now the rate of heat flow, that means this dq by dt, mathematically, if you like to express the mechanism that is going on in DSC, then you can write it in this fashion. dq by dt is equal to Cp into beta into W, where W is the sample mass, beta is the heating rate, and Cp is the specific heat at constant pressure, and this is the heat flow. Now this is expressed as joules per second or watts. So let's write it down, the expression once more. You have dq by dt is equal to Cp beta W. So this is joules per second, this is in grams. So your dq by dt by W is equal to Cp into beta. So this what is given as milliwatt per gram, that we can see in the y-axis, and this is the temperature. Now So if the value is negative, we are having an endothermic process. That means where the heat is being absorbed by this material. And if the value is positive, we are having an exothermic process, that the heat is given out of this material. Now, there are mainly in polymers or in sometimes in metals, the important properties that is used, that gets determined through DSC is, as I have told you, is we find out delta HM, or enthalpy due to the melting enthalpy. It's also called enthalpy of fusion that take place, and another process, that is the crystallization. Does delta HC enthalpy of crystallization. These two processes are determined through a DSC plot. Now let's take an example. Let's take an example of a polymer called polypropylene. In short, it's written as PP. Has the structure like this. You have CH, CH, C, H, H. This is how the PP propylene looks like. Now, taking a DSC plot of propylene, the shape is something like that. You have a heat flow in the y-axis, which is watt per gram, and you have temperature, and the temperature has been taken up to 250 degrees centigrade from 0 degree temperature. Now here the DSC plot is being measured in two different runs. That means the first run is when we are increasing the temperature. So the plot will look something like this. It will show a downward peak. This is the run 1, and then we have run 2, which will show an upward peak like this. Now this is from 0 to 250 degree and then back. So run 1 is where we are heating that polymer to 0 to 250 degrees centigrade, and then run 2, when we are cooling it, we are taking it back again to not 0, 25 degrees centigrade room temperature. Now these peaks obtained in DSC, if you take the slope of the peak region, this one, this area inside the slope, it gives you the delta HC, or the enthalpy for crystallization, and it takes place and it is around this delta HC for polypropylene is approximately 91.86 joules per gram, and the temperature at which this occurs is 122.35 degrees centigrade, and this is obtained in the run 2, where we are cooling it. And similarly, if you take the area of this peak region, it will give you the enthalpy of fusion, or the melting enthalpy, and this enthalpy of fusion is 75.89 joules per gram, and it occurs at about 161.25 degrees centigrade. So this one is due to crystallization and this is due to melting. So these are the usefulness of a DSC plot. Now, when you have this information, when you have, for example, delta HM, another parameter that can be determined from this delta HM is the degree of crystallinity, how much the crystalline the material is, and that is expressed as Xc percentage is equal to delta Hm divided by 1 minus phi delta HMO, where phi is the weight fraction of the matter, and delta Hm is the enthalpy of fusion if 100% melting has taken place. So if all the material has melted, then the enthalpy required is delta Hm. Now, as I mentioned in my previous class, that this enthalpy is the most important parameter when we are considering the rate of reaction. So you must remember that the rate of reaction is reaction rate is proportional to exponential minus h by RT. So this is that's why this enthalpy plays a crucial role in any phase change that is taking place. Now, another important property that is obtained, and it is basically a routine check in case of polymers, that property is called oxidative induction time. Oxidative induction. Now let me remove all this. It's called oxidative right. Oxidative induction time. In short, you can call it as OIT. What is actually OIT is that when you are allowing the material, when you are applying some sort of heat to the material, the time you provide basically an inert nitrogen gas, where the material by absorbing the heat it starts to melt. Now when it starts to melt, it shows a sharp transition, and at this point of time you stop this nitrogen gas and you start giving an oxygen gas, and so at this point the material starts to decompose. And this is a practical test which is used to find out the stability of a polymer. Now the usual plot of an oxidative induction time test is like this. You have time in the x-axis and you have heat flow in the y-axis. So instead of temperature you have time now, and the plot usually takes the shape like this. We have an right. This is how the plot looks like. So initially there is an exothermic reaction, as you can see, and at this time, at this point of time, this is how the decomposition is taking place, the fusion is taking place. Now when at this point we are supplying oxygen, previously it was nitrogen, now we are supplying oxygen, and this time is the OIT. When this is the point where the material has started to decompose. So there is an another starting of another peak is the indication that the material has started to decompose. So from melting region where the melting is complete to the region where the decomposition starts to take place, this time is the OIT, and this is very important for the case of polymers, and it's a routine check done for the polymers.